So this is lecture 1, and this is going to be on the Galerkin's method, a introduction to Galerkin's method, and we're gonna do this easy. Basically, we're gonna look at functions, how we can approximate functions. So let's say we have this domain between A and B, and we denote this domain by the Greek letter capital omega here. Now, we know a certain function here which we want to approximate. So this is just some general function u of x. And this function is going to be approximated by another function of our choice somehow, anyway we want. So we can do something like this and call this capital U of x. So this is the approximating function that approximates u of x. So we're saying that, all right, we want to approximate u of x. We want to approximate u of x with capital U of x. No, the other way around. We want to approximate u of x like so. Okay, so the problem statement that we want to look at is find u of x such that and now we have to have a measure. So find u of x such that, how are we going to formulate this so that we get a best approximation? I mean, we could do it. We could say that, all right, we can look at a number of intersection points and have as many of them as possible. So at these, obviously at these intersection points, we have that u of x is exactly capital U of x. So the approximation is exactly the same as the actual function. But on average, it's the error between these two functions is going to be big. So the keyword is on average. And average means some sort of area. So we're looking at basically the area between these two functions right here. So we have, let me color this in. We have probably smaller and change the color to blue. So we have this area here that we want to minimize. So if we find a function which creates the smallest possible area between u of x here and capital U of x, then we have the best approximation on average. And that's what we want, that's what we're after. So our formulation thus states that find u of x such that the area between u and capital U is as small as possible. Alright, so obviously we can choose the same u if we knew it, but in general we do not know u. So that's why we need to find an approximation. But then you should ask yourselves, alright, so if you don't know u, how could we possibly calculate the area? Because we need u to know, to know how to calculate the area. And that's what we do. We pretend that we know u. And we want to approximate it with another function, u. Alright, so what we're saying is, let's pretend that we know u and we want to approximate it with another function. We can look at what type of properties this function will have later. Okay, so now we look at the form which capital U should take. So u of x is chosen to be on the form that is u of x is approximated by capital U of x, which is u1 times this basis function phi1 plus u2 phi2 plus and so on until ui phi I. Okay, so this is a sum I from 1 to n u1 phi 1. It's a linear combination of several basis functions, and these coefficients here, u1, u2, and u3, and so on until n amount of these coefficients, and we can choose how many we want. We can say, all right, we want only one, and that would be a constant function, or we can have two, and that's a linear function, or we can have three, and that's a quadratic function, or and then so on and so on and so on. So we can choose what the polynomial order of this function is. And yeah, sure, we could use another type of function, logarithmic, sinusoidal, exponential, but we use polynomials because polynomials have certain properties that we very much like, and we'll get into that later. But basically, it's very easy to integrate, it's very easy to differentiate. That's basically why we choose polynomials. There are other methods which utilize other linear combinations of different functions, but then there are completely different methods. So for instance, you have, if you have sinusoidals and you have an infinite amount of them, that's another method which is well known as the Fourier series. So you have that method, but in this course we have a finite set of linear combinations, and there are polynomials because for integration reasons that we will get into later. Alright, so this is the form of the approximation. Right, now we need to formulate more rigidly what this business means here by finding u such that the area between u and capital U is as small as possible. What we're going to do is we're going to state this like so: find ui such that we minimize the residual, and that's r of x, which is basically just the difference between them. So u of x minus u of x. Of course, if we do this pointwise, you will see that we get the same curve back, but it will not be possible to do it pointwise for every point, because we typically choose approximations of a lower order. So we can use any polynomial, right? So why don't use the 100th order polynomial? We don't typically do that. What we do is we choose first, second, third order. And most often it's first and second. But yeah, in general we can choose anyone that we like. So what is going to happen? The thing is, let's do an example. Let's do an example to show this. So example, let's say we use a linear function. So then we will have u of x. By choosing a linear function, we are basically setting phi1 and phi2. So let me write it like this: we have u1 phi 1 plus u2 phi 2. Okay, so we're making this choice. We have thus chosen a linear function or linear approximation, and that is our choice. Alright, so this means that u of x is going to be u1, and then this function, if it's a linear function, I'm just going to throw this at you in this region. Let me first do the region, and then our region is here. this is A and this here is B, and then our approximation is located on B, on A and on B. So let me actually take this further up. So somewhere here, and this is these points that I'm drawing here are U2 and U1, and we need to find these. So these are, you can imagine these being sliders, and you are choosing them by you know, just sliding them across here until this area, which these this blue line forms with the actual function that we want to approximate here, u of x. So this area here needs to be as small as possible. So we are going to find u1 and u2 such that this area is as small as possible. All right, between A and B, and which defines our omega here. Okay, so given this choice, then we can know what phi 1 and phi 2 is in terms of A and B. So this will look like the following function. We have u of x, which is u1 times phi 1, and phi 1 looks like this, b minus x over b minus a. Then this is phi 1, and then plus u2, and then we have x minus a over b minus a. And these guys, this is phi 1 and this is phi 2. And I'll get in a future lecture into details of how you construct phi 1 and phi 2. Okay, so in this case, this is linear interpolation. This is what we have created here. So we are linearly interpolating a function between u1 and u2. All right, what about the area? Well, the area becomes, the area is thus, can do a is equal to, and then we have the integral from a to b, and then we have r of x times a weight w here times the x, and we set this equal to 0. Alright, so we're not looking at the absolute value of the area, we are looking at the residual basically. So basically it's like looking at like this. We have this is a plus area and this is a minus area here, and we are trying to find where this area is 0. So where the area on top of this line and below this line is the same. So basically we're saying it's the signed area, if you want. It's not the total or absolute value of the area, because that's always going to be non-zero. Yeah, we can look at that like that as well, but it's much easier to formulate this type of area. Otherwise, it would look like this, and this would definitely not be equal to 0 ever. And then we would try to minimize this, but it's easier to just formulate this and set it up as a equation. And if you find this, we have minimized the area. Much easier than formulating it as a minimization problem, especially since you haven't done a course in optimization probably. So this is how we're going to run this. Now let's look at details here, because I've already hinted that r of x is equal to u of x minus u of x. So let's continue with that. So we have r of x equal to u of x minus u of x. Okay, so if we expand this now, because we know what u of x is, we have it up here, so we can write it on a general form. It's the sum of I equal to 1 to n ui phi I minus u, right? Just omitting the of x part here, just to make it a little bit more cleaner. Right, so minimizing the area A means finding which UI are minimizing it. It's basically like sliding these guys around here until this area is as small as possible graphically. So this method is called the weighted residual method. So this is the weighted residual, and this is a umbrella term for different types of optimization methods. There are several options for this choice of this residual here, W, and the most common one is the so-called Ritz method. So in here we have several methods, and one of them is, let's do it here, it's the Ritz method, but you will probably know it under a different name. It's the least square method, least squares method. So if you did this in mathematics, you'll probably have fiddled around with the least squares method, and maybe in different ways, maybe in a computer lab or something like that. But basically how it looks like is it's the following. So we are minimizing something, so minimizing s, which is 1/2 of the integral from a to b r of x squared dx. So that's why it's called the least squares method, because we're squaring r of x, the residual, and then this is minimized, which is minimized by the following, by letting we let the derivative of x of s with respect to ui, hold on, the derivative of s with respect to ui, we let this be 0, and from this it follows that wi is the derivative of r with respect to ui, and from this we get that the integral from a to b r of x times this weight here, which is dr the ui dx, is 0. So that's the least squares method, where we have the derivative of r with respect to ui. But the Galerkin method is another weighted residual method. So now we're going to look at that. Alright, Galerkin, or rather Galerkin, which is a Russian engineer, proposed that this weight should be the actual derivative of the basis function instead of r. So the Galerkin is a variation. Galerkin method is a variation of the Ritz method, or least squares method. So instead of differentiating this here, r with respect to ui, because it's hard, right? What is r? Let's take a look at r. So r is the true solution, right? R of x. You have the true solution, and you're probably confused now by this. Like, why is u here? We don't have an idea what u is, and we're trying to approximate it. What's happening? And that's the thing, that we will break things out, and then this will become more clear. But we don't want to have this dependency on ux in the actual minimizing of the approximation. So that's why, for that reason, Galerkin proposed to, alright, let's use a different weight here. So instead of having a function r, which depends on the true solution, he proposed to do to use the actual basis functions here, because there's no dependency on the true solution anyway here. What Galerkin proposed was to use, so instead, let me do it like this, instead of differentiating R of x, differentiate the approximation u of x. Okay, so basically it looks like this. The dui of u1 phi 1 plus u2 phi 2 plus and so on. Thus we get that the weights wi of x is equal to du of x over du I. And if you look at it, you're going to differentiate away all the u's, the small u's, so you will get back the actual function phi I of x. And in this simple case, both of these methods will coincide. So both the Ritz method, the least squares method, and the Galerkin method will produce the same approximation. Okay, finally we can state our what the Galerkin method is. So thus the Galerkin's method states find ui such that the integral from a to b r of x times phi I of x dx is equal to 0 for I equal to 1, 2, and so on until n. And this is the Galerkin's method, which we shall be using throughout this course, and for more things than just approximating curves or functions, I should say. We're going to use this for differential equations in our next lecture. But we're not done. Let's see this in action. So let's take an example. So consider a function u of x. Let's just keep things simple. U of x is equal to x squared in x, or let's do it like this, for x in 0 and 1. Okay, so let's do a graph. It's always nice to visualize this. So we have this thing, u of x, like so. And then somewhere here we have our function, our approximation. And yeah, well, I can tell you now, we are going to approximate this with a linear function. So example, consider a function u of x is equal to x squared for x 0 to 1. So we are 0 to 1 here, and find the best linear approximation for this function. So that's the problem statement. Find the best linear approximation. Okay, so that means that we are going to find a linear function that perhaps looks something like this. So this thing is capital U of x. And of course we are looking for the beginning and end point here, u1 and u2. Okay, so we can now formulate our question like so. Find u1 and u2 such that, and then we can do this, r of x phi I of x dx is equal to 0, where where r of x is of course u of x minus u of x, and phi, I can do it here, phi 1 of x is again, we have it up here, b minus x over b minus a, which is 1 minus x over 1 minus 0, and phi 2 of x is a minus x over 1 minus 0, or b minus a. Okay, so the first function here is of course 1 minus x, and the second one here is minus x. Did I do this wrong? Yeah, it's the other way around, sorry. So this is x minus 1, x minus a, or x minus 0, which of course is just x. So this is how it looks like with phi 1 and phi 2. Okay, so u of x, let's take a look at the u of x then. U of x becomes what? Well, it's just u1 times 1 minus x, which is phi 1, plus u2 times x. So that's our linear approximation. So now we are looking for u1 and u2 such that this integral is 0 for I is equal to 1 and 2. Okay, so now we can now find u1 and u2 by the integral from 0 to 1, r of x, which is u of x minus u of x, this times phi I of x dx. Okay, and this becomes the integral from 0 to 1, and we have u1 times 1 minus x plus u2 times x, and all of this is multiplied by no, we can do it like this. So this is u minus u of x, and then all of this is multiplied by phi I of x dx and set to 0. Okay, so for I is equal to 1, we have our first integral, which is 0 to 1 u1 times 1 minus x plus u2 times x minus u of x, and then we can actually substitute what u of x is, which is just x squared, like so, and then all of this is multiplied by the first basis function, which is 1 minus x dx, set it to 0, and then the second integral, I is equal to 2, states that 0 to 1 u1 times 1 minus x plus u2 times x minus x squared times our second basis function, which is just x. So just to clarify, this is phi 1, this is phi 2, this is u of x, and all of this is u of x u of x. Okay, I can continue. Dx is equal to 0. Okay, what do we have here? Well, we have two equations and two unknowns. And that's u1 and u2. Thus, the system is solvable or has a unique solution. Okay, now I'm not a fan of solving things by hand, not even this simple, so I'm just going to switch to MATLAB here, where I've already started doing this. So I stated the problem here, which is missing the true solution, which is u of x, so which is x squared. So I'm just going to insert this here and here, just to be consistent, like so. And then we have our true solution here, which is u is equal to x squared, like so. So we have the approximation, we have the true solution, we have our basis functions. Now we can formulate this system. So I'm gonna make things a little bit more compact and do equations, and then I'm gonna make a list. So basically I'm saying, all right, I want to integrate int, and what I want to integrate? I want to integrate u minus u, and then this stuff here, put that in parentheses, and multiply that by phi1, like so. And let me see here. Yeah, I can get rid of that. And another parenthesis to close this up. And in here, this is the second argument for integrate. I can check how the syntax should look like here. So the expression and the variable, and in this case I want to make a definite integral, so I'm doing a and b as well. So expression, variable, and a and b. So my expression is x, because I'm integrating with respect to x, and I'm integrating from 0 to 1, like so. And then I'm gonna set this to be equal to 0 explicitly, like this. If I don't do that and I send it to solve, it's gonna automatically assume that I mean that it's supposed to be 0. So I'm not gonna make a mistake, but I would like to make things more explicit like this. So the second one is going to be multiplied by phi2. That's the only difference. And now if I run this, MATLAB will do this for me, this integration, and this is what I will get back. So now I have a nice system of two equations, which I just can send to the solver and get u1 and u2. So I can do like this, u1 and u2. I can state what output I want, and then I send this to solve, and I tell it I want to solve these equations, and then I need to state in what order I want or actually what it's going to solve for, what variables. And if I omit this, it will still work, but the order is going to be arbitrary. So u1 might not be u1, it might flip this around. So by doing this explicitly, you're telling MATLAB to give you the output in a proper way. And this is the sort of true solution then, or I mean the values, the nodal values for our approximation. Okay, let's not stop here. Let's plot this thing to really show what's happening. So what I can do here is I can say, all right, give me a figure. Well, it's not necessary to do this, but yeah, it's good practice. So figure and function plot, fplot, and x squared, and then the range. So this is going to be from 0 to 1. And you know what? I want this to be red. So I'm saying color, and I'm doing R for red. So here's my graph of how that looks. Now I can pimp it with X labels. You can say that this is X and Y label is Y. Okay, now for U, if I just type out U, it's not going to be substituted with our solutions here. So we might do that with subs. It's going to substitute. It's going to look, okay, what does U contain? U1 and U2. Okay, are these variables set? Yes, they are. Let's substitute them. It's not going to override them though. So this is my final linear equation. And now I want to plot it. So if I just do fplot and subs U like so, from 0 to 1, it's going to actually override my old graph. So I'm going to show you this. Color blue. Okay, in this case, actually, yeah. If I use the live script, it's going to create another graph, and I don't want that. I want it to put one above the other. So in order for it to do that, I do hold on. So it's going to hold whatever graphics is in the first one and then plot above that. And now again, to know which one is which, I can do legend, and I can just say that, okay, first one is U of X, and the second one is capital U of X. Like so. And this now is the best linear approximation for x squared in the range of 0 to 1. If we look at the integral between this region here and this region here and this region here, it's going to be 0, because this is positive, this is negative, and this is positive. And we can verify this, right? Because we can do the integration. So if you do int and we just take, now we have to use the subs U, we can actually overwrite this. We can say, okay, U is equal to subs U, and then it's overwritten. And we do U minus U. And we do this for X between 0 and 1. And this integral is going to be 0. Right? And because, you know, one is positive, the other one is negative. If we want to take the absolute value of this, we can do something like, well, we can do abs. And now this is the total value for this integral, the total area, the total visible area, let's say. And we can, this is not a numeric answer now, so what we can do is do VPA. We can wrap this around VPA and then tell it how many values or how many significant numbers we want. And then we have it here. So this is the actual unitless area that is visible, the white space here, if you want. So that's the difference between integrating the absolute value and just integrating the residual. So the residual is 0 because this is what we have done, we have minimized it, and then this is the actual white space. Good. So this is a complete video of how to do this. What else can be said? Well, if you go back, I can tell you that, yeah, so choosing this approximation that we have done now here, choosing this approximation is of course not the only option. We can go higher and add terms to this and make it quadratic and cubic and even higher, right, as I told you before. and we will look at how to create basis functions phi I later. So for now, you can just accept that this is a linear function, but later you will actually see how these should look like for any function that you want, or any polynomial function that you want. Okay, let's do another example, just to make this video very complete before we go to differential equations in the next one. So, example 2. Let's approximate using a second order polynomial, or aka a quadratic approximation. On the same interval. So let's approximate u of x is equal to x squared using a second order polynomial. What's going to happen? Now we need to have the basis functions for a second order polynomial, and I'm just going to throw these at you, and for this range, these are the functions that you want, and we will later look at how these are actually created. So x1 is going to be 2 times x minus 1 times x minus 1/2. Phi 2 is going to be minus 4 times x minus 4 times x minus 1, and phi 3 is going to be 2x times x minus 1/2. Now take a look at these. We have 3 basis functions now. Why? Well, because remember, if you go back to how these look like here, so we have u1 plus phi 1, u1 plus phi 1 plus u2 times phi 2 plus u3 times phi 3. So we have 3 terms for a quadratic or a second order polynomial. We could have a 0 order polynomial as well, and that would just be a constant function. So if you look at the graph for a for that type of thing, we would just be looking at a constant like that and try to fit that curve in so that the area is 0, and that's very useless, really. So second order curves are defined by 3 points, basically. That's what we are looking at. Yeah, so that means finding the best u1, u2, and u3. Okay. So our approximation is thus: u of x is equal to, or is approximated by, capital U of x, which is the sum I is equal to 1, 2, 3, and we have u I phi I. This is what we're doing. We will get 3 equations. that look like this. The integral from a to b. I'm going to do this general again and then substitute. We have u minus u times I can do it like this. I times phi I dx is equal to 0 for I is equal to 1, 2, and 3. Okay, again, because we have three equations and three unknowns, means unique solution. Alright, so let's do this in MATLAB. So I'm gonna do Control Alt Enter to make a new section here, and in this section I'm just gonna throw this up here. Alright, so we have our integral 0 to 1 capital U minus U times phi I, and actually omit this subindex I here. It's really not useful because these are not varying by I. For the approximate solution, we have U here, which is U1 phi 1 plus U2 phi 2 plus U3 phi 3, so it's quadratic, 3 terms. And our basis functions look like this, which is phi 1, phi 2, and phi 3. So I'm putting that as a vector. So this is a vector here containing these three functions. And then, of course, this is what they are. And this really needs to be transposed, like so. I'm just putting it like this. It's easier to read. And these here are only valid for x in 0 to 1. I could have written this more general, but then these equations will be very, very long. So I'm gonna use them here for 0 to 1, which is a typical space or region, but we'll get to that later. Okay, now your three equations will look something like this, and we shall now see what these are if we write them up in MATLAB. So again, we do clear, and then we are defining our symbolic variables. So we have u1, u2, u3, and we have x, and these can be real. But let's see what, because we use real up there. Let's see what happens if we omit real here. Really nothing, but I'm just gonna show you so you can see various ways of doing this. And remember, if anything is unclear, write it down, ask me later. Okay, so this is what we will have now, and we will formulate our u, which will be, well, we need the basis functions first. So I'm going to do it like this. I'm going to do phi is equal to, and I'm going to create a list of these equations, like so. 2 times parenthesis x minus 1 times open parenthesis x minus 0.5, and then the next one down here, which is going to be minus 4 times parenthesis x minus 1, and the next one here, 2 times x minus 1/2. Okay, and I run this, and of course I need to transpose this because this needs to be a row matrix. So I can do transposing by typing dot and then this, oops, this here, which is well, it's this symbol here anyways, so you can take a look at it later. You'll find it on the Swedish keyboard. You will find it between shift and enter on the right hand side. It's underneath the star. Yeah, anyhow, this dot here just makes this behave as a standard transpose instead of a conjugate transpose. If we just use this, we will get conjugate transpose, and you will see this by x being having this bar on top, and that's a conjugate transpose. It doesn't really matter if x is not a complex number, and we're not dealing with a complex number, and that's the only reason we put real here, is just to get rid of that bar, because now all of these variables are defined as real numbers. They cannot be complex. So this is an assumption you are sort of putting into that. And that's just how MATLAB works. I personally prefer having real here because it's gonna simplify solutions in some cases. It might be that it's assuming that stuff is very general and it gives you a much more bloated solution than it needs to be. So real is simplifying certain things here much easier, and also means that I don't need to put this dot before this transpose character here. Alright, so now what I can do is with phi here is I can define my I can define the function u, which is going to be u1, u2, u3. So I basically have u1 times phi 1. So I could, if I want to, I could do this like this and then do phi 1 here. So I'm selecting from this vector, or from this matrix, really, I'm selecting the first element. So I'm selecting this stuff here. So if I just do that just to show you, this will work. But I much more prefer to do it like this: u1, u2, and u3, and then multiply this with phi, because, or rather the other way around, to make it as a matrix multiplication, like so. Right, because this is a row vector and this is a column vector, and this multiplication here will yield a scalar, which is exactly what I'm looking for. So that's my preference. You can do this however you want. I'm just showing you other methods. Okay, so now we have u. Great. We need to define the exact solution u, which is x squared. There we go. And we are basically ready to define our integrals. So again, I can do int, or I can define the stuff that is inside this integral as u minus u, and then times phi, and then this is the first one, like so, and then integrate around this. Say this is x, and then so from 0 to 1, and then I will get the output like so. I can do this, or I can just omit this 1 here, and it will do this 3 times, once for each, and this is very hard to read, so I like to just transpose this, and then I can get the output like this. So this is my equation system. So I'm inserting a vector in here. That means that this whole thing will run 3 times for each vector, and that's a vectorized operation. It's a functional programming paradigm, if you want. And again, you can do this however you want. If you find it easier to do it in a different way, to have 3 separate integrals, by all means do that. I'm just saying that this is an alternative way of doing it vectorized. Okay, so these are now my equations. Right, I have 3 equations and I have 3 unknowns, so this means that this problem is solvable. And then I want to have u1, u2, and u3 returned by solve. And I'm sending in equations, and I'm telling it what I want and in what order. Always mess this up. Like so. Alright. And again, now I'm just going to go back in here and copy some of this code. This is what I want to do. And yeah. So figure f plot u from 0 to 1, color red. This, hold on, substitute u. So it's going to take u and substitute u1, u2, and u3. And it's going to plot it with the blue color and get the legend. So let's run this. And what happened? What happened? I just got a blue line. Why? Take a minute and think about this. Obviously, I'm plotting both of them. In fact, I can show you here by doing Control R to commenting this out. And if I'm running this, this is the red one, and I omit hold on, and I plot the other one, so I will have two of them, and here are both of the plots. So obviously I'm getting there, but what is happening here? Well, what happens if we just look at the substitute of u? If we just write it out above here. So now we're substituting u. So let's look at that. Okay, this is the output, right? So it's just taking u here and it's substituting these values, but it's not simplifying anything. All right, we can do that. It's not just by hand, we can actually simplify in here as well. And what do you think is going to happen, just given that it has plotted these on top of each other? And also, here's another hint. We are approximating, we are finding the best fit of a quadratic to what? A quadratic. This is a quadratic equation here. And we're trying to approximate this using another quadratic. I hope that hint gives you the answer. This is just simplified back to x squared. Because if our function that we want to approximate is of the same order, and using Galerkin's method we are finding the best fit, then of course we will get back the same equation. We will get the best possible equation, which is a quadratic equation. So this is indeed what is happening here. We are getting back the same equation which we started out with. So I mean, in general, when you will be doing this, you will be you will most probably never going to approximate true functions like this. They will always be more complicated, but theoretically it is possible to find a fit that is very good. And in general, also theoretically, any function can be approximated by a infinite series of polynomial functions. The problem is that becomes computationally unfeasible to do. So in practice, that's never done. Instead of finding a best fit in the whole region from 0 to 1 for a complicated function, what we're doing instead is we're not solving the whole thing, the whole region. We're not fitting one approximation for the whole region. Instead, we are breaking these regions up into smaller pieces, finite elements, and we are finding the best fit for each of them. And then the solution will be a piecewise approximation. That's indeed what we're going to look at in the next lecture. So hopefully you will have learned something, and you need to work on your work package, because learning is just one part of learning is just watching a video, but the other one is actually getting your hands dirty while doing this. So get working, and see you later.